right. Hi, everybody. This is a class for my 30S Pre-Cal students. And this is a lesson that's not really in your notes booklet. It's not even really a lesson. We're just going to go over some examples and use technology to help us solve equations. So I'll do these questions. I'll do them all kind of twice. Once with the graphing calculator, because I do have a few people in my two classes that have an old graphing calculator. And we'll use Desmos as our kind of main tool. All right, so let's look at number 13. The height h in meters of a flare, t seconds after it's fired into the air, can be modeled by this equation. At what height is the flare at its maximum? So basically what we want to do with this equation is we want to find its vertex. Without technology, our only strategy would be to complete the square or to use minus b over 2a and then plug that number back into t and then figure that out. And since these are kind of nasty decimals, that's kind of an unfortunate bunch of calculations. It does say verify your solution with or without technology. We're just going to do it with technology. So at what height is the flare at its maximum? So basically when you launch a flare, it's going to reach a maximum at some point, and that maximum is its vertex, right? So we are going to try, let's do the graphing calculator first. So let me see, let me get the graphing calculator going. It's on the bottom menu, there it is. And let's move it over, and then it disappears because it's like that sometimes. There we go. Okay, move over. Move. There. Oh, it still doesn't want to go over there. There. Let's try that. Okay, so let's turn it on. Clear whatever we were doing. Is there any graphs already in here? Nope, good. You always click the y equals button to look for your graphs. Okay, so now we're going to enter this equation. So it doesn't matter, there's a button here that says xt theta n. It doesn't matter what the actual variable you use is. But please notice it is important that you recognize that a calculator needs to be told the difference between a subtract and a negative. So I'm going to use my negative button, negative 4.9 times x to the power of 2, so that's squared, plus 61.25 x, and then I'm ready to graph that. Now if I hit graph, I've got a stat plot on. I forgot I was doing some statistics with people, so I've got to go to stat plot and turn that off. Actually, I might have to just clear that. There we go. And enter and graph. Okay, that's still going to be clear. Now let's graph. No, that's still not going to go. Okay, I'm going to have to get out of here. Stat plot, off. And go to, sorry. Okay, hold on a sec. I might have to reset the calculator, and that might kick me out of my program here. So I'll be right back. Okay, we're back. I did not have to actually restart all my programs to reset the calculator, which is good news. But I did have to kind of do a bit of a reset on all the plotting because I had something from a stats class in there. A good rule of thumb is to check stat plot and make sure that all of the statistics functions are not graphing anything, because these calculators can't graph a statistics like a bar graph and a polynomial equation at the same time. So that was the problem. So go now to this graph and hit graph, and there it is. Oh, that's not very exciting, is it? And the problem is that I'm looking at my usual window from negative 10 to 10 for x and negative 10 to 10 for y. And I mean, look at the equation. You have to have some sort of kind of awareness of what your equation is. Well, it does have a y-intercept of 0, but think about how big this number is. Chances are we're just not looking at a window where we can see it. So we have a couple things we can do. We can go to zoom, and if you click down to zoom 9, there we go, zoom 0, sorry. Zoom 0 is zoom fit. And if you hit enter, there we go. Now, the graphing calculator is just doing its best to try to fit the graph onto the screen. So that's why zoom fit is what that's called. And it thinks it did a good job for you. It's very proud of itself right now. It doesn't realize that in this situation, none of those negative numbers mean anything. But it did give me kind of a place to start, right? Now I know roughly where the graph is. So now I'll go to the window and I'll play with it myself. So the window, I obviously don't need to go to negative anything. Having said that, I actually don't like looking at these graphs and having my axis right on the edge of the screen. So I'll give it a little bit of negative, like negative 0.5 or something. And then the x maximum of 10 wasn't quite big enough to see the entire graph, so maybe I'll go to 12. I'll still count in ones. And now notice the y minimum. They go way down there. I don't need any negatives for y, so I'll go negative 1 or something. And then the y maximum is 191. I'll just round that to a nice even 200. And then I'll graph it again. And there. Oh. Having said that, I think I still need a little more room on my x. So I'll go to 15, say. Graph it again. And there we go. We have completely got the graph. Now, what is it that I want again? I want the vertex. So I go second function, calc, and I'm looking for my maximum, right? Because it's an upside down parabola, so the vertex is the maximum. So I click 4, and then again, it's going to want a left and right boundary because I might be graphing something that has more than one maximum or minimum, right? There could be local maximums and minimums. So this thing's designed so that I have to kind of give it a range of data, or a domain of data. So I'll go past it on the left, hit enter. I'll go past it on the right. Oops, oh, and then of course my clumsy hand didn't do that properly. I'll go past it on the right, and then I'll hit enter. It's going to ask if it wants me to guess, if it wants a guess, or if I want to guess, and I'm going to say no. Please calculate, don't guess. Even if it takes a second, and it did, and there we go. We have ourselves a maximum at x equals 6 I'll just ignore all those decimals, 6.25, comma, and 191.40625. So 191.40625. So what do those two numbers mean? Well, look at the question they asked me in A. I actually have both of those answers, which one's which. There you go. So the maximum height is y. Height is a function of time x. So this is the height answer. So I'll say, therefore, maximum height is 191 point, and I don't know, do I need this many decimal places? It is in meters, so here's the nearest centimeter right there. That seems pretty accurate. If I rounded it to 6, that'd be the nearest millimeter. I don't know who out there needs to know where a flare is in the air up to the nearest millimeter, but not me. And then, therefore, the maximum occurs at 6.25 seconds. Would make sense. I don't think you'd see a flare in the air for 6 minutes. So there we go. So there's the first one. That one's pretty easy. All I had to do is figure out how to graph it. And on Desmos, here's the way this would look on Desmos. So on Desmos, I would go. I can still use h of x, but I'll use x instead of t. And it knows that it's a function. And then I'll type in negative 4.9 x squared, and then plus 61.25x. And I have the same problem that I had with the calculator. It's like, well, there's your graph. Doesn't look very parabola right now. But if you have a touch screen, if you're using a smartphone or a tablet, you can, of course, just grab it with your fingers and keep kind of stretching it till you see with the parabola you want. Unfortunately, it does it in both directions. So there, I fit the thing on the screen, but it's awfully skinny looking. To get around that, the best way to do this is to play with the window setting again. So I'll go to here. It's already, the y-intercept's fine, the y-axis is fine, but the x-axis, again, I don't need to go to negative 200 and something. So put the cursor there and just backtrack to negative, I don't know, negative 5. Again, I just don't like my axis to be right on the edge of my screen. And what did we say? 15 was, I think, a pretty good. There we go. And there it is. Boom. And when you click on it, it will just tell you. Actually doesn't give you as many decimal places as the graphing calculator did. But it's still accurate to the nearest millimeter, which seems pretty reasonable to me. Okay. What if it had asked you how long is it in the air? What would you do then? Obviously, it was fired at time 0. What are you thinking? Find the other x-intercept. And the other x-intercept here is 12.5 seconds, so there you go. This thing was in the air from time 0 to time 12.5. All right, so that's the first example. I'll just erase that. And when you want the grid to return to normal, you hit home. And there you go, we're back to negative 5 to 5 and 10 to negative 10. And let's try another one. This time they don't give you the equation. You got to build it for yourself. 3 rectangular areas are being enclosed along the side of a building as shown. There is enough material to make 24 meters of fencing. We've seen ones kind of like this before. So if I'm making a enclosure, obviously there's a wall here, so there's the side of a building, so I don't need to put fence there because the building is the fence. But if this thing's rectangular, then D is how long all of these sides are. There's 4 lines that are D units long, which means what? Well, if these are all D's, how long is it from, say, here to here? Well, let's see. We started with 24 meters of fencing, and then we used D of it to make that line, that row. We used D of it to make that row. We used another D, we used another D. We've used up 4D. So you know how much is left to make this? 24 minus 4D. So now, write a function that represents the total area. So how much area is there in here, right? How much space does this thing cover? The space in there. And to do that, you have to think, well then I would like length times width. So the area as a function of line D is length times width. I'll put the width first. Width times, and again, this line here is 24 minus 4D. And that's actually good. That is an equation. It's good to go. It's in function notation too, because it did want a function. But I have a feeling my answer key, because I peeked at it already, is going to want this in standard form. So multiply that out, and this is the way they give the answer. They give it as negative 4D squared plus 24D. And there's A. Now, how do I know that this is a quadratic function? Well, because its biggest power is a squared. And then graph the function, explain which strategy used. Well, the strategy is I'm going to use technology. So once again, I'm going to go to my Desmos. And I would like A as a function of x is minus 4x squared, and what was it again? Plus 24x. And once again, we got that same problem, so I'm just going to move this over and then play with the intercepts here. So I don't need to go all the way to 18. It looks like if I go to 7, I've got plenty of space to see the graph. And the height going to 11 is not high enough. Let's see, what if we go to 30? 30 something. Nope, not high enough. 35, not high enough. 40, winner. And there we go. There's our graph. Okay, so now what is it actually asking for? It says graph the function. I did that. What are the coordinates of the vertex is the next question. And click on the line and it'll give you 3 points usually. The vertex, actually it'll usually give you 4 points. It'll give you the vertex, the x-intercepts, and the y-intercept. Now that's assuming that there are x-intercepts, right? Not every parabola has that. And of course in this case it only gives 3 points because the y-intercept is one of the x-intercepts. It goes through 0, 0. But there we have it. What was this number again? 3, 36. So let's go back to the question. So okay, so we did our sketch. We did A and B, we did C. What are the coordinates of the vertex? Well, they are, so this is question D. They are 3 and 36. And what do those things represent? So what does the 3 mean and what does the 36 mean? 3 is the length of fence side D, otherwise known as the width. And 36 is the maximum area resulting from D. Okay, now, you are used to looking at parabolas and saying domain is just negative infinity to infinity, easiest half mark there is ever going to be on any of my tests. Now, that's not really accurate. I mean, take a look again at the graph. It does go on forever past those 2 points, but in the real situation, is it reasonable that D could be a negative number? No, are you going to build the fence into the wall? I don't think so. So D is going to be bounded by 0, and it looks like 6. So I would write that as my domain. So this is me doing domain. So my domain, I like interval notation, goes from 0 to 6. My range, again, if I have 0 distance, I have 0 fence for area, but the absolute maximum area was 36. So there you go. So domain gets a little bit harder than it was in chapter 3. We have to think about the situation and what makes sense. And does the function have a maximum value? It does. So for question F, it's 36 meters squared of area. Does it have a minimum value? I guess you'd probably say 0 meters squared, right? I mean, I don't know why you'd build the fence right up against the wall like that, but I guess you could if you wanted to. And what assumptions are being made? Now, I am assuming that D can be any real number. That's definitely an assumption, right? I'm assuming that I could measure D to be pi units long if I wanted to, because that's in the domain. It could be decimals that I round it to and measure it to. Okay, so there we go. So there's the next question. All right. A stone bridge has the shape of a parabolic arch as shown. Determine a quadratic function to represent the shape of the arch if the origin, A, is at the top of the opening under the bridge. So I'm going to have to use maybe a different color here because this is black. Let's use red. So what if my origin is right there? What is the equation of this graph? Okay, so let's think about this. Anytime you have a parabola where its vertex is on the origin, what do you know? Well, if your vertex is on the origin, this is of course a parabola, then at the origin, H and K are 0. So that means that we have y equals A times x squared. Now what do we know about A? Well, we know A is negative, right? A should end up being a negative number. But we're going to have to figure out some way to find A. How are we going to do that? Well, if that point that I made in red is 0, 0, then this point that I'm going to make, say, in purple here, is 20, comma, negative 12. Where did I get that point from? I'm imagining this is my grid. Here, I'll do it in red again. I'm imagining that I made a grid, and, oops, I missed 0, 0. Make a bigger dot. There we go. And 0, 0 is that spot there. Notice, I know a parabola has to be symmetrical, so if it goes 40 across here, this has to be the point 20, and it goes down 12. So there we go. I can now use this point to find A. When y is negative 12, x is 20, and A is going to be negative 12 400ths. I'll probably go to a decimal on that. 4 goes into the top 3 times, and 4 goes into the bottom 100 times. So that's negative 300ths. So my final answer for A is negative 300ths x squared. All right. It is kind of, in a question like this, totally arbitrary where you put 0, 0. They didn't assign you a grid. You had to superimpose a grid on top of this bridge and decide for yourself where the origin is. What if I made a different assumption? What if I missed some, hold on. What if we put the origin on the ground at the midpoint of the opening? So what if the origin is right here? Now, H and K aren't 0 anymore. So now my equation for B is going to be y equals A, and my vertex has moved. It hasn't moved horizontally, so H is still 0. But K has done what? What has K done? It has gone down 12, but my vertex, if this is 0, 0, the vertex is above it. So to go from 0, 0 to where the vertex is, it's a shift of positive 12. Do you see why that has to be a positive number? Now, I have good news for you. Do I have to recalculate A? There's people go, yeah, okay, let's pick another point compared to where that 0, 0 is, run it through the formula, and find A. That's a waste of time. Who can tell me why that's a waste of time? Because A represents the shape. I'm just moving the vertex around. Is the shape changing? Not at all. So the answer to B is negative 0.03 x squared plus 12. So there's my A answer. There's my B answer. All right. I think you've been watching me here all passively. Your turn. See if you can figure out C and D. I'll pause the video. Try C and D for yourself, and we'll come back and go over them in a minute. And we're back. Okay, so if the origin is at the base of the bridge on the right side of the opening, so if the origin is right here, so now to get from there to this vertex, what do you have to do? Well, A, as we've already kind of realized, is not going to change. But now, to go from this point to that point, I have to move 20 units to the left. Remember the opposite rule for that? And 12 units up. Okay. And then for D, so this is the C one. And then for D, what if this point was on the left side at the top surface of the bridge? So, okay, I'm not sure exactly what they mean by that, but I think what they mean is this corner here. Is that the way you interpreted that question? the left side, the top surface of the bridge, right? Because this is the surface of the bridge, right? There's cars driving, there's the car driving, right? So there's the top surface of the bridge. So I think they mean there. Okay. Well, does the shape of the parabola change? No. So A is still negative 0.03. But now, how far do I have to move to get to this point here? I have to move half of 56, which is 28, but I'm moving to the right. And then I'd have to move down how much? How much do we move down to get from this point here to this point here? The answer is 3, because it's 12 for the arch height and 15 to the top of the bridge. So minus 3. And there we go. So that's a good question. I like that question. Okay, I got one more for you, and then we'll let you guys have some work time. A store sells energy. We've seen one kind of like this already, if you did your homework. The store sells energy bars for $2.25. At this price, the store sold an average of 120 bars per month last year. The manager has been told that for every 5-cent decrease in price, he can expect the store to sell 8 more bars monthly. What quadratic function can you use to model this situation? Use an algebraic method. Actually, we're going to use a graphical. Use graphical method to determine the maximum revenue. Okay, what's revenue? Well, revenue is the money you take in. It's not profit, it's the money you take in. What's revenue based on? Well, it's based on the price times how many you sell. So let's write that down. Revenue is equal to price times units sold. That sounds very business-like. All right. What do we know about this situation? Well, first of all, we have to define an X. What is it that we're trying to measure? We want to know what to set the price at. Now, what are we changing? X is going to be the thing that's changing. We're changing how many decreases in price. He's talking about reducing the price to try to sell more, but obviously if he reduces it too much, even if he sells a whole lot, he's going to lose money. So we're going to let X equal the number of 5-cent decreases. Okay, so right now, my R function is price times units sold. So right now, price is $2.25, but we want to decrease by 5 cents, but we don't know how many 5-cent increments to decrease by. So price is $2.25 minus, now careful, I can't say 5x here because this is in cents and this is in dollars. So I have to go 0.05x, right? My new price. If I decide to decrease it once, my new price is $2.20. If I decide to decrease it twice, my new price is $2.15. I'm counting my decreases in increments of 5 cents. Why would a store do that? Well, because maybe they like the idea of the price not, being countable with change, and we don't have pennies anymore, so we have to deal with 5-cent nickels, right? So there we go. There's price. Now, times, let's use a different color, units sold. What does units sold look like? Well, right now, it's 120. But for every 5-cent decrease, we're going to gain 8 more sales. So I sell 120 normally, but I'm going to increase that. For every decrease in 5 cents, I go up 8 sales. Now, that is a quadratic equation, kind of in factored form. Not quite factored form. But one of the great things about using technology is, if the numbers are really ugly and you don't feel like foiling this out and working with them, you can actually enter this exactly the way it is. So you can see why for the applied course, where people's algebra skills and arithmetic skills might not be at the level of you guys here in the room in pre-cal, this is the way we teach it. We'd say, you can stop there. You don't have to simplify it. You don't have to FOIL it out. Let's just go to our grapher. So I'm going to go back to Desmos. I'm going to erase that guy. And I'm going to type in my equation. Now, it doesn't matter what we call our equation. Again, I could call it a function. Oops. Hang on. There. Revenue as a function of how many decreases is, and the formula we got was 2.25 minus 0.05x, close the bracket, open the bracket, and the amount we're selling, normally we sell 120, but we gain 8 every decrease. So plus 8 times the number of decreases. Close brackets. Once again, it's graphed and I can't see it. So I'm going to play with my screen. And oh, there it is. There we are. Good enough. This time I don't think I need to set the settings. We're good. Now, obviously, this whole side of the graph over here is kind of meaningless, right? My revenue would be 0 if I sold them for, my revenue would be negative if I gave them away and sold them for nothing, right? So we don't care about negative revenue. So we are looking for the maximum revenue. So we want that point there, and it turns out that it's 15,360. So go back to the graph here. So my vertex is, and that's how good my memory is. I have already forgotten the number I just looked at. 15,360. Okay, we got it. 15,360, 15,360, 15,360. Now, what do those two numbers mean? This is the number, right? That's X, right? So that's the number of 5-cent increases. And 5 times 15 is 75 cents. So in other words, the best price to set it at is 75 cents more than what it was set at before. What does this number represent? Revenue, but not just any revenue. It's the highest possible. It's the maximum revenue. So if I want to set the price, so 15 times 5 is equal to 75 cents, right? I should say 15 times, put that in cents, 0.05 is 75 cents. So the original price was $2.25 plus 75. Oh, sorry, minus. You're right. I'm sorry. You're right. Minus. We're decreasing the price. Thank you. So $2.25 minus 0.75, because we're decreasing that much, is actually, let's see, what would that be? Take away 25 and you're at $2, take away, so it's $1.50? Somebody double check my mental math. And somebody, hey, pen, come back. Every once in a while the pen decides to freeze on me. There we go, $1.50. And you know, the other place you could get this number is to just go back to here and plug in your X of 15. So therefore, a maximum revenue of, what was the revenue again? $360 happens when the price is $1.50 per, I've already forgotten what we're buying here. Energy bar. There we go. All right, so there we go. Maybe just before we leave this one example, I did it with Desmos. Let me show you one more time how to do this. You can enter it just like this on the graphing calculator as well. So let's go back to the graphing calculator. Go back, turn it on. Go to the plot list, erase what's there. Type it in exactly the way it looks on the screen. 2.25 minus 0.05x, close bracket, open the next bracket. 120 plus 8x, Close that bracket. Graph it. I said graph it. Can't see nothing. So go to zoom, and then I think it was zoom 0, right? Or zoom 10, which they just go back to 0. So zoom fit. And again, is it gonna do it? It's actually, oh, there it is. And again, well, nice try, calculator. We'll give you that you definitely showed us a curve. Good job. But that gives us at least a starting point. Basically double my x value, and I think we're there, right? So go to x of, say, 30. Let's go 35 and graph it again. And there it is. And then we would like to find the vertex. So we go second function, calculate. It's a maximum, so you have to hit 4. You have to, right now my cursor is too far to the right, so move it to the left. You can see that it starts going down, so you know that you're to the left of it. And then enter, and then move the cursor to the right until it goes past its peak and starts going down again. There we go, we're definitely going down. Enter. No, we don't want to guess. And there it is. There's the same 360 and 15 that we got from Desmos. All right, you can have some time to work on these now. That's the video.